The next presentation will be given by Dr. Artem Panchenko from Tel Aviv University.
So this is quite special cases that that we considered. So I will not stop on motivation of this work. Previous talks notice the importance of ballistic transport for nanoscale levels, and this work is a continuum of work made by Kuzkin in last year, and here we considered not out of plane but only in plane motions of graphene atoms. So there is infinite ideal crystal lattice. A particle could move only in plane, and equation of motion in harmonic approximation in vector form you can see here, and scalar form you can see on this slide. So we have four. So it was continuous of this work, and we considered in plane motion. So this is equation of motion in vector form and in scalar form. So for two atoms in unit cell. So we have two springs, axial and torsion spring. And to get analytical solution, we need to obtain dispersion curves of this system by solving eigenvalue problem. And when we get dispersion curves, calculate group velocity, and then we can calculate these integrals to obtain evolution of thermal profile. So for molecular dynamic simulation, we considered periodic boundary condition and integrate. So this is dispersion curves, and this is analytical solution for evolution of temperature profile. And for molecular dynamic simulation, we use periodic boundary condition, integrate equation of motion by leapfrog algorithm, and the main problem is averaging results by a lot of realization. So we use GPU calculation to reach enough performance. Okay, the first task was evolution of sinusoidal temperature profile along X or Y direction, and calculate amplitude of this profile. So this is analytical solution, and this is the results. And you can see that there is exact matching between line of analytical solution and points averaged by 10,000 of realization. So the second task was spreading of hotspot in graphene. So this is analytical solution, and it has this form. So to compare with previous work, we have a spike on the center, but 6 spikes around the center, and these lines, 3 lines. So for molecular dynamic simulation, you can see that matching is good, and only for averaged results. So between one realization and analytical solution is not much common. And it should be noticed. It should be noticed that it is significant anisotropy of velocity in lattice. So along these two lines, most of kinetic energy concentrate on x direction, and along this line, most of kinetic energy concentrate in one y direction. So here you can, I will show the video, this one. This is the results of evolution of hotspot, and temperature is normalized by maximum on the each frame. So if we construct a temperature profile along middle line, we will get a very good agreement between MD and analytical solution. But except except this part, and I think it's connected to slight difference in time between analytical and MD, because this part is oscillating very fast. So I think it's quite results. We get a very good agreement between analytical solution and MD simulation for ideal harmonic lattice. I think that's all.
Okay, thank you very much, Artem. So questions, comments, please. Okay, so let me start probably. At slide number 15, I think you have shown component Y and X. So here, what do you mean by X component and Y component?
It's square of the velocity along X direction and Y direction.
You mean that at those points,
yes, mostly
X temperature and Y temperature are different?
Yeah. So the most kinetic energy concentrate on X direction and Y direction.
So in general, temperature is a tensor in this case, right?
Yeah.
Oh, that's very interesting. Okay, thank you.
And maybe I will ask, did you try to separate in optical and acoustic modes?
No. I think it's quite difficult for MD simulation. I don't
yeah, in MD
sure
it's very complicated.
Did it.
What about analytical? In analytics, it's easy.
No, we don't. But I think it's quite. If we compare to your results, it will be these 4 pikes is acoustic, and these lines, because they are very fast, I think they're acoustic too. And this pike is optical, maybe.
And sorry, another question. Did you try to compare with the result of MD simulations of Ilya Brukhanov, which were presented before at the previous session?
Not yet, but as you can see, it's a lot of common, but a lot of difference. So I have the same pike on center, but it seems for another pike are quite similar to the center pike. So this is the difference.
Well, would be very interesting to check.
Yeah. Maybe we could compare 3D harmonical and 3D real, let's say, potential calculation.
May I ask a short question?
Yeah.
Yes.
Before I start. So, Artem, and what is the formula for the temperature? Is it the same for out of plane vibrations, or is it a different one? Your analytical formula.
Yes, it's quite the same, but it uses different eigenvectors and group velocity.
Mm-hmm. And different dispersion relations.
Yeah, yeah.
Okay.
Okay. Any
Thank you.
further questions, please? Okay. I don't see any more questions. So thank you very much, Artem, again.
Thank you.